So, next one we will take few example, right. Next one is that calculate that this example 2, calculate the capacitance to neutral per kilometer with and without considering the effect of earth, right. Radius of the conductor is 0.01 meter, space 3.5 meter apart and 8 meter above the ground. Also compare the result, that will compare the result means with and without their effect of the earth, right. So, here no need to draw the your what you call that conductor configuration, right. So, it is you apply equation 44. So, that is basically C12 is equal to 0.0121 upon log divided by log d upon r into 1 plus d square upon 4 a square to the power half microfarad per kilometer. R is given 0.01 meter, d is also given, the spacing 3.5 meter and height 8 meter, that is the conductor height from the ground, this is given. So, here you C12 when I am writing C12 earth, because this equation actually when effect of the earth is considered. So, 0.0121 divided by log 3.5, that is your d, then r 0.01 bracket 1 plus 3.5 square divided by your 4 into h 8 square to the power half. This comes actually 0.00477 microfarad per kilometer, right. And if it is your C1 to 2, that is between two conductors, but if it is neutral, C1 earth is equal to C2n earth is equal to 2 C12. This formula you have seen earlier, C1n is equal to C2n is equal to 2 C12, but effect of earth is considered. So, that is why C1n bracket I writing earth, C is equal to C2n in bracket writing earth is equal to 2 C12 earth. So, this is the C12 value. So, it will be multiplied by 2. So, it will be 0.00955 microfarad per kilometer. This is the value when effect of earth is considered, right. Now, for line to neutral capacitance without considering the effect of earth, you apply equation 10 already derived. So, it is C1n is equal to C2n is equal to 2 C12 is equal to 0.0242 by log d upon r, right. So, microfarad per kilometer, d is known 3.5 meter, r is 0.01 meter, right. So, you will get 0.00951 microfarad per kilometer. Therefore, you take the ratio C1n earth divided by C1n. So, C1n earth we got this much, this is C1n earth we got this much 00955, right. So, if you take the ratio, it will come 1.0042, that means presence of earth increases the capacitance by 0.42% only, which is negligible. That means presence of earth increase the capacitance, but that increase is negligible, right. So, this is that your what you call that that means for all the practical purposes for computing capacitance, one can ignore that effect of your what you call that earth, right. Perhaps you will find similar findings for the 3 phase also. So, that is up to you. I have given that thing that you should derive that, right. Next you come to another example, example 3. So, in that case you determine the capacitance and charging current of a 200 kilometer long transposed double circuit 3 phase line as shown in figure 11. That means, this is your figure 11, right. The line your operates at 220 kV and radius of the conductor is given 2 centimeter, right. So, this is that your what you call, it is given that your line is your transposed. So, this is the configuration we have just now we have derived all this your expression, right, for the 3 phase double circuit transposed line, same mathematical expression we will use. So, D1 is given 7.5 meter, this is actually given, right. D4 also given 9 meter. Here if I try to make it here, it will become very clumsy, and r is equal to 0.02 meter. These distances are given, and this distance, this height from here to here, this is also given 4 meter. That means, here to here 4 meter, here to here also 4 meter. That means, here to here 4 meter, here to here 4 meter, right. So, accordingly you have to calculate all other distances. So, if you apply equation 35, that is CAN is equal to 0.0242 divided by log dq upon ds microfarad per kilometer. This is actually from equation 35, right. So, d1 is given, that is 7.5 meter, then d2 is equal to root over 4 square plus 8.25 square, right. So, from here also, from here you can find out what is your d2, right, what will be your d2. So, this height is your 4 and d4 is given your what you call d4 is given 9 meter. So, from that you can find out that what will be your d2, right. I mean, you take like this, make a right angle triangle and then calculate the distance and make it. So, d2 is equal to 9.168 meter. So all these things I have told earlier, again I am not telling that how this 0.25 will come, right. So, this is just you make it, no, all if d1 is given 7.5 and d4 is given 9 and this height is 4, from that easily you can find out what will be your d2, right. So, next is the d3. Similarly, d3 also will be root over 8 square plus 7.5 square, right. It will become 10.965 meter. Calculate d4 is given 9 meter, d5 will be 8 meter, because this is the vertical height. So, here it is 4 plus 4 8 meter and d, and similarly calculate d, this d both are same. So, but you calculate this d, it will be 4.07 meter, right. So, first all these distances you compute, right. Therefore, from equation 38 we have seen that dq is equal to d to the power 1/3, d2 1/3, d1 1 to the power 1/6, d5 to the power 1/6. So, substitute all these values, right. So, you will get dq is equal to 6.61 meter, right. Similarly, from equation 39 already we have derived, we have ds is equal to r to the power half, d3 to the power 1/3, d4 to the power 1/6. Substitute r, d3 and d4 here. So, 0.02 to the power half into 10.965 to the power 1/3 into 9 to the power 1/6 meter. That will give you ds is equal to 0.453 meter. Now, CAN will be now that formula 0.0242 divided by log 6.61 upon 4.453 microfarad per kilometer, that is equal to 0.02078 microfarad per kilometer, right. Now, line length is given 200 kilometer. Therefore, CAN the total will be 0.02078 into multiply by 200, it will give 4.157 microfarad, right. Now, magnitude of the charging current, I am putting mod I charge, CHG means charging current, is equal to omega into CAN into V line to line voltage. Capacitor is your phase to neutral. So, that is why it is also voltage should be taken as line to neutral magnitude, right. So, line to neutral voltage is in general Vn angle 0 degree, if Vn is the reference, the mod of VLN is equal to mod of Vn is equal to 220 upon root 3 kV, because it is 220 kilovolt line. So, it is line to neutral voltage. Therefore, magnitude of charging current is equal to 2 pi f, omega is equal to 2 pi f 50 hertz system into 4.157 in 10 to the power minus, it is microfarad, that is why it is 10 to the power minus 6 farad into 220 upon root 3 kilo ampere per phase. That means, I charging current, that is magnitude of charging current will be 0.1658 kilo ampere per phase. That means, charging current actually is not very small, that is equal to 0.1658 kilo ampere per phase, means 165.8 ampere, right, per phase. So, this is how to calculate the charging current, right. Now, next one is you have a different configuration. So, this is figure 12, this is figure 12. So, figure 12 shows the conductor configuration of a bundle single overhead transmission, single phase overhead transmission line. The line is operating at 132 kV and 50 hertz, right. So, this is a 132 kV line. Radius of each conductor is given 0.67 centimeter both side, right. Here also radius 0.67, this side also, right. Find the equivalent representation of the line and capacitance between the line. You have to find the equivalent representation as well as the capacitance of the line. This is actually equilateral triangle, because D all distance same. So, this is equilateral and this is horizontal spacing, right. So, in this case your capital D, right. So, this D, that means A2 to this is actually, let me tell you, this is 3 conductors are there in phase A. So, bundle conductor. So, A1, A2, A3, and here 3 conductors are there horizontal spacing B1, B2, B3, right. And distance between A2 and B1, I mean from here to here, it is given as D, right. So, this distance is D is given, that is a 6 meter, that is given, right. Here in the numericals, here I have not written all this, but this D is given 6 meter, and D is equal to your what you call this D is equal to also given, it is 0.1 meter, this is given, and R is equal to 0.67 centimeter, that is 0.0067 meter, that is the radius of the conductor of this one, this side as well as this side, right. Then you have to find out H is equal to, this is that H is equal to, find out this the height you this you find out, because this you require actually, right. So, if you find out, so you will find root over it is 0.1 square minus 0.05 square, because D is equal to your what you call 0.1 meter, this D, right, 0.1 meter. You draw a vertical line here, right, and that means that is your H. So, H is equal to root over this distance square D square and minus D by 2 square. So, 0.1 square minus root over 0.05 square is equal to 0.0866 meter. So, this is your H, right. Next, you have to find out that DSA and DSB, right. I mean self GMD of this side as well as, this is for line A, this is for line B. So, this side you have to find out. So, basically it is this configuration actually series equilateral triangle, right. So, DSA, that is your DSA, that will be for this one actually R D square to the power 1/3, right. For a, so, you need not consider because it is a symmetrical spacing and equilateral triangle, just one conductor you make it. So, one is your in general you know that it will be, if you consider this conductor, it will be like your D A1 into D A1 A2 into D A1 A3. So, D A1 is R and D A1 A3 is D, and this is also D. So, R D square to the power 1/3, because 3 distances, right. So, that is actually DSA. So, is equal to, similarly for here all will same. So, ultimately if you take R D square into R D square into R D square to the power 1/9, so ultimately it will become R D square 1/3, right. So, 0.067 into 0.1 square to the power 1/3. So, 0.0406 meter, right. Similarly, for this one also it will become DSB if you take any one. So, DB if you take this one, it will be DB1, right, DB11 into your DB12 into DB13. If you repeat for other two also, it will be same. So, that is why directly you can write that other one, that RD R into D into 2D for when you consider your B1 B2, right. Similarly, if you first one is this is your DSB. So, DB if you consider DB1 your B2 BB1 B1 rather. So, it will be R, then B1 to B2 into D and B1 to B3, it will be 2D, right. This is one. Then we to sort of mid conductor, it is DB2 B2, that is R, and DB2 B1 D into B2 B3 also D, right. Similarly, when you come to this one and this one same. So, it will be r into d into 2d to the power 1 by 9, because 3 3 3. So, altogether 9 combinations. So, it is 3. So, n square it is 9. Here it is symmetrical, that is why we are writing 1 by 3, but here it is not symmetrical, right. So, it will be r d into 2d into r d d into r d into 2d, right, because B 1 to B 3 or B 2 3 on this one and this one product same. So, to the power 1 9. So, upon simplification it will come r to the power 1 third into d to the power 2 by third into 4 to the power 1 by 9, right. So, in that case it will become 0.00671 third into 0.12 third into 4 to the power 1 by 9, because 2 into 2 4, that is why separately taken as 4 to the power 1 by 9, right. Therefore, DSB will be 0.0473 meter, right. Now you have to calculate DEQ, that means all sort of combinations you have to take, right. Here also 3 conductors, here also 3 conductors. So, 3 into 3 9, that means all possibilities will be you have to consider. So, DEQ is equal to DA1 B1 into, just for your understanding, everything has been made it here, DA1 B2 into DA1 B3. Next you consider A2, DA2 B1, DA2 B2, DA2 B3. Next you consider A3, DA3 B1, DA3 B2, DA3 B3 to the power 1 by 9, right. So, all these distances you can compute D1 B1 how much, 6.1 meter. All these distances you please all the preliminary things I have made it here, all these distances you can easily compute, right. So, if you compute, because previously I have shown how to make all these things, right. So, DA1 B1 will come 6.1 meter, DA1 B2 will come 6.2 meter, DA1 B3 will come 6.3 meter, right. Now, DA2 B1 will be 6 meter, DA2 B2 will be 6.1 meter and DA2 B3 will be 6.2 meter, right. So, once you similarly, this is straightforward. Now, similarly, if you consider DA3 B2, it will be, I mean DA3 B2 means you make it there and this will be right angle triangle, right, all these things you calculate. Similarly, DA3 B1, again you from here to here you compute, and similarly your DA3 B1 and DA3 B3, DA3 B3, DA3 B2, DA3 B1, all these 3 cases 3 right angle triangles you make and accordingly you calculate, right. So, DA3 B2 will be 0.0866 whole square plus 6.15 whole square to the power half, it will be 6.1506 meter. Similarly, DA3 B1 0.086 whole square plus 6.05 whole square to the power half, 6.05606 meter. And similarly, DA3 B3 is equal to 0.086 whole square plus 6.25 whole square to the power half, 6.2506 meter. Now, then this DEQ in this expression, you substitute all these distances, right, all this data you substitute. So, all have been substituted here, to the power 1 by 9. If you calculate, DEQ will become 6.15 meter, right. So, your that means it will be 6.15 meter. So, and next is your what you call then what will be the equivalent configuration. Equivalent configuration is that distance for DSA and DSB you got. DSA you have got 0.0406 meter, right, as if this is the radius of one conductor, right, which is equivalent to this bundle conductor, right. All these 3 conductors there is equivalent radius will be 0.0406 meter for this group, right. That means line A, 3 conductors are there on equilateral spacing, right, and this horizontal spacing. Similarly, your DSB is equal to your 0.0473 meter. So, as if this side can be represented by a single conductor whose radius is 0.0473 meter, right, and distance between two, that is DEQ is equal to, we just computed here it is DEQ is equal to 6.15 meter. So, this is equivalent 6.15, this is the equivalent configuration. Now, I have a question to you. Now, although we are using bundle conductors, radius is very if you take its radius is 0.67 meter, right. And here if you take, of course, you can see that here it is 0 this thing what you call 0067 and it is 04, radius has increased, but instead of using this equivalent thing we use this one. There must be some advantages, right. So, this is a question to you, what are those advantages instead of making this kind of single conductor configuration, right. So, this is the equivalent configuration, right, as if to the single conductor, right. So, now applying equation 7, you have CAB is equal to pi epsilon 0 upon ln d root over R A R B. In that equation it is given pi epsilon 0 d upon root over R 1 R 2, if I recall correctly, farad per meter. You can go back to the equation 7 and it will be taken like this. So, substitute this thing, instead of d I can make it is dq, right. So, this will be pi and epsilon 0 is the 8.854 into 10 to the power minus 12, right, and ln your 6.15 divided by R A root over R A into R B, that is your basically dSA into dSB. This equation actually there should not be any confusion, right. This equation, that equation 7, can be written as, this is equation 7, it can be written as CAB is equal to pi epsilon 0, right, ln dAQ by root over dSA dSB, right. This way it can be written. That is why this is actually equivalent RA and RB. This is from here I am writing this is equivalent RA and RB, that is nothing but this is DSA and this is DSB, right. So, therefore, if you make this one you will get that your 0.00562 microfarad per kilometer. So, I hope you have understood this, right. How to make all the thing is that calculation should be be careful of calculating all the distances correctly, right. The next one is that find out the capacitance of the line as shown in figure 15. This is figure 15, right. The radius of each subconductor is 1 centimeter, right. So, A B C, A dash, B B dash, C C dash, that means in each phase 2 conductors are there and horizontal spacing, and between these 2 conductor distance is 0.6 meter, right, and between this any 2 phase conductors A dash, B dash or B dash, C dash, it is 6 meter, right, these things given. So, you have to find out the line capacitance. So, R is equal to given 1 centimeter is equal to 0.01 meter, ds easily you can calculate, R d to the power half is equal to, you will get 0.07746 meter, DEQ will be DAB, DBC, DCA to the power 1/3. Now, you know how to calculate AB, BC, CA, DAB, DBC, DCA. So, it will be DAB is equal to DAB, DAB dash into D A dash B dash into A dash B into D A dash B dash to the power 1/4. DAB 6 meter, D A dash B dash 6 meter, DAB dash is calculated root over 6 square plus your 0.6 square. So, all these things you calculate, all the distances you calculate, and you will get D and D A dash B also, D A B dash and D A dash B is equal to 6.03 meter. This is also same 6.03 meter, right. And DAC is equal to DA dash C dash is equal to 12 meter, and DAC dash is equal to DA dash C is equal to root over 12 square plus 0.6 square is equal to 12.015 meter. From this configuration, you can compute all, right. Therefore, DAB you calculate, it will become 6.015 meter, and DAB from the symmetry DAB is equal to DBC, right. So, it is same. So, it is 6.015 meter. only dCA you have to calculate, dAC into dAC dash into dA dash C into dA dash C dash to the power 1 by 4, all combinations. I told you one inside find out all combinations and to the power 1 by 4, because in each phase 2 conductors are there. So, when you considering the your mutual distances between them, so combination will be 2 into 2 4. So, it is 1 by 4. Substitute all these distances, all you have got it. It is 12.0075 meter, right. Therefore, DEQ directly that formula all DAB, DBC, DCA, DAB, DBC, DCA to the power 1/3, it is coming 7.573 meter. Then apply equation 34, you will get CAN is equal to 0.0242 log DEQ upon DS, right, is equal to microfarad per kilometer. Substitute DEQ and DS, right. If you solve, you will get 0.01216 microfarad per kilometer. So, all the varieties of problems I showed, and another one it is not a difficult one, but a simple one, that derive an expression for the charge value per meter length of conductor A of an untransposed 3-phase line as shown in figure 16. I will show you the figure 16. The applied voltage is balanced 3-phase. Also find out the charging current of phase A, right. So, you have to derive an expression of the charge value per meter length of conductor A of an untransposed 3-phase line as shown in figure 16. The applied voltage is balanced 3-phase. Also find out the charging current of phase A. You have to find out the charging current of the phase A. So, this is that. This is the configuration, horizontal configuration. Radius of each conductor is R, right, and this is A, B, C. Distance between this your D, any two your phase conductor D, here also D, right. So, earlier you have seen that your VBC, VCA and VAB, right, for line to line voltage, right. So, this we have seen, and accordingly we have, when you see VAB plus VAC is equal to 3 VAN, when we prove that, at that time we have seen same diagram. This is your VBC, here it is B is the tip, because this VBC arrow is here for BC, right, VAB, and similarly your VAB. So, this is VAB, that means parallel to this VAB, parallel to this VAB, A is the tip, and this is VCA, C is here, VCA, C is here, right. And when you it is a balanced system. So, when neutral is here, when you join this all this thing, this is VAN, this is VBN and this is VCN, right. So, this VAN, VBN, VCN, just put it here, VAN, this is VAN, VBN, this is VBN, and VCN, this is VCN. So, this way first you make this phasor diagram, that means if VAN is the reference, if VAN is the reference one, that means VAN is equal to V by root 3 angle 0 degree, because we assume VAB, magnitude VAB is equal to magnitude VBC is equal to magnitude VCA is equal to V, right, line to line voltage magnitude. Therefore, my VAN will be V upon root 3 angle 0 degree, because if we take VAN as the reference, right. Therefore, your VAB, that means VAB will be V angle 30 degree, because VAB actually leading VAN by 30 degree. So, VAB is equal to V angle 30 degree. VAB case, it is line to line voltage, this line to line voltage leading this your what you call this voltage VAN by 30 degree. So, VAB is equal to V angle 30 degree. Similarly, VBC, that is your VBC actually from VAN, it is lagging by 90 degree. That is why VBC is equal to, it is line to line voltage. So, no question of root 3 here or here, VBC is equal to V angle minus 90 degree, because it is lagging from this, right. And similarly, VCA is equal to V angle 150 degree, right. That means, this is VCA, this between VAB and VC is 120 degree plus 30. So, 150 degree, that VCA is leading VN by 150 degree, that is why I have written VCA is equal to V angle 150 degree. And similarly, VAC, your VAC will be V angle minus 30 degree. It is CA. If you want V, because this is needed, VAC will be V angle minus 30 degree. The reason is simple. Suppose this is your VAN, this is VAN, this was your line to line voltage, say VCA, right, and this one your VBC. Now, it is VCA. If I make it other way, so it will be VAC, just CA AC 180 degree. That means this angle is 30 degree, right. That means your VAC is lagging, you are lagging from VAN by 30 degree. That is why VAC is a line to line voltage. That is why VAC is equal to V angle minus 30 degree. That is why you have taken VAC is equal to V angle minus 30 degree. So, it is understandable, right. So, okay, thank you.